Good morning all. In this class we can start with the sample and hold circuits. We have already discussed about sample and hold circuits. A sample and hold circuit samples the input signal and holds on its last sample until the next sample. So it's useful for digital interfacing circuits, ADCs and pulse code modulation systems. So here shows the digital processing system. So actually our signal available is an analog signal. So if there is a plant, by using a sensor or transducer, we have to convert it to an electrical analog signal, and it is passed through an anti-aliasing filter, and so band limited analog signal is sampled and held for analog to digital conversion. Yesterday we have seen that a discrete value of 10.8 volt is sampled to is digitally converted to a digital code of 1011. That means it takes some time to convert from 10.8 volt discrete analog value to this digital code. So we have to, after sampling, that signal have to hold for some time. Okay. So for this we are using sample and hold circuits. So here shows an analog signal. It's a continuously varying signal with respect to time, while here shows the sampled signal, or which is a discrete signal. At a regular intervals, we are taking the samples and hold it for the time intervals. So here shows the circuit diagram of sample and hold circuit. So basically this consisting of an N-channel E-MOSFET, that is enhanced MOSFET N-channel. So enhanced means it is a normally off MOSFET. The MOSFET will turn on when the control input is given to the gate. So here, since it is an N-channel, of course, when if you are using a square wave, when the signal is high, when the control voltage is high, the MOSFET turns on, and when the control voltage is low, the switched MOSFET turns off. And here there is a capacitor to hold the discrete instantaneous value. Okay, so there are two more components like voltage amplifiers, one at the input side and the other at the output side. So if there is input side, actually this voltage amplifier, it's for an voltage amplifier, input impedance is very high, while its output impedance is very low. So that these amplifiers voltage followers are used to isolate the sample and hold circuit from the other circuitry, basically. So here, since its output impedance is very low, the charging time of this capacitor is the output impedance of this voltage follower plus the on resistance of the MOSFET. Okay, while since its input impedance is very high, this time constant is not affected by the high input impedance of the op-amp. And here at the output side, we are again using a voltage follower, which used to using a voltage follower. Since the input impedance is very high, this capacitor cannot discharge during the hold time. And since it is a voltage follower, whatever be the input voltage will appear at the output also. Here also the input voltage will appear at this point. Okay. So the circuit consisting of N-channel E MOSFET as a switch controlled by a control voltage and a capacitor stores the charge, two voltage followers, one at the input and the other at the output. The input analog signal to be sampled is applied to the drain of the MOSFET and control voltage to its gate. When PC is positive, the MOSFET is on, the capacitor charges to the instantaneous value of Vi with the time constant R0 plus RDS on into C. So R0 is the output impedance of the voltage follower, RDS on is the on resistance of the MOSFET. When Vc is negative, MOSFET is off and the capacitor holds the value of Vi for further processing. The capacitor cannot discharge due to the high input resistance of voltage follower A2. So here shows the waveform of different waveforms. If assuming this is our input signal and this is the control voltage, the square wave, and when during the high signal is actually the charging sampling time, and this is the hold time. So at this during the sampling time, actually the capacitor charges its the maximum to this last value, and it will hold that value for hold time. So in order by this time, the ADC can convert to a corresponding digital signal. So by this, we have completed the 6th module. Now 5th module is again a portion in the 5th module. So PLL. It is phase locked loop. Phase locked loop is a frequency selective circuit designed to synchronize with an incoming signal and maintain synchronization in spite of the noise variations in the input signal frequencies. What are the applications of PLL? Basically, PLLs are used for satellite communication systems, radar synchronization, and airborne navigational systems, and FM communications systems, computers, etc. So basically, a PLL consisting of a phase detector or a low pass filter and a voltage controlled oscillator, and in between the low pass filter and VCO, usually we are having an error amplifier also. That block is not shown here, an error amplifier also. So usually, as you know, at the receiving system, the incoming receiving frequency is usually emerged in noise. So actually, by using a PLL circuit, we can clean up the incoming signal frequency. So what is a voltage controlled oscillator? Voltage controlled oscillator is basically a oscillator which having a free running frequency of omega naught. But unlike other oscillators, actually this oscillator is having an input that we can give some DC voltage as its input. So according to the DC input voltage, of course, this VCO can vary the frequency frequency of operation from its free running frequency. Okay. So this is the voltage controlled oscillator, and it is consisting of a phase detector and a loop filter. So phase detector means there is an incoming signal frequency with a phase of theta I, while VCO is having a frequency of theta 0. So phase detector detects the phase difference between theta I and theta 0 and produce a DC signal as well as some more frequencies. So loop filter is usually the output of phase detector consisting of some frequencies and the difference frequencies. Okay. So the difference usually that loop filter out the all higher frequency ripples as well as the noise and all, and pass out only the DC signal, that is VE. That means when omega 0 minus omega I is equal to 0 or DC, that means actually this PLL locked with the incoming signal frequency. That is omega 0 is equal to omega I എന്ന റേഞ്ചിലേക്ക് എത്തി. So that after locking condition, the PLL can synchronize with the input signal frequency and follow the input signal frequency. So the phase detector compares the phase with the incoming signal frequency against the phase theta 0 and develops a voltage proportional to difference theta I and theta 0. And VD is sent through a low pass filter to suppress high frequency ripples and noise, and the result called a error voltage VE is a P and is applied to the control input of the VCO to adjust its frequency. So VCO is designed so that V is equal to 0. It is oscillating at some initial frequency omega 0 called the free running frequency. So its characteristics is omega 0 of t is equal to omega 0 plus k0 V of t. Okay. K is the sensitivity of the VCO. It's represented in radians per second per volt. So this k0 into VE actually K0 into VE actually gives radians per second. So this will add up with the pre-running frequency. If the input is applied with the frequency omega I sufficiently close to omega 0, the error voltage VE will develop, which will adjust omega 0 until V0 is synchronized with VI until for every input cycle. There is one and only one VCO cycle. So PLL is now locked with the incoming signal and gives out omega 0 is equal to omega I exactly. If there is a change in omega I, the phase shift between V0 and Vi will start to increase, changing VD, hence the control voltage VE. This change in VE is designed to adjust VCO until it is brought back to the same value omega I. A PLL can be designed to lock on the incoming signal in spite of the noise. A noise input will generally cause the phase detector output VD to jitter around some average value. So if the filter cutoff frequency is low enough to suppress this jitter, PE will emerge as a clean signal, in turn resulting in a stable VCO frequency and phase. We thus use omega 0 as the output of PLL whenever we wish to recover a signal buried in noise and also in frequency related applications such as frequency synthesis and synchronization. So consider the phase detection being accomplished with the balance. Of course, PLL is very similar to balanced mixer. As you know, a mixer output consisting of some frequencies, difference frequencies, that is omega I plus or minus omega 0. But in the case of mixer, omega I minus omega 0 is also a DC signal, while here the different signal is 0 or DC. So low pass filter suppresses the sum but passes the DC component, thus keep the loop in lock. If the loop is not locked, the difference frequency falls above the cutoff frequency of the filter and it will be suppressed along with the sum frequency. Okay. No output leaving the loop unlocked and oscillating at its free running frequency. Okay. If omega 0 is sufficiently close to omega I to make the difference, the frequency approach, the filter band edge, a part of this component is passed and tending to drive omega 0 towards this free running frequency towards the incoming signal frequency. As the difference is reduced, more error signal is transmitted to the VCO, so resulting in a constructive effect. It is actually a negative feedback, okay, which brings the PLL in lock. So here we are having lock certain definitions, lock range and a capture range. The capture range is the frequency range centered about omega c, that is plus or minus omega c centered about omega 0, over which the loop can acquire lock. This range is affected by the filter characteristics. Okay. While lock range or hold-in range is the frequency range plus or minus omega L centered about omega 0, over which the loop can track the input, hence lock has been established. So the lock range is affected by the operating range of the phase detector and the VCO. And some time it takes for the PLL to capture the incoming signal. So that time is called a capture time or pull-in time. This time depends on the initial frequency, phase difference, and DI and D0, as well as the filter and the other loop characteristics. Okay. So these are the basic building blocks of PLL: phase detector or comparator, VCO, low pass filter, and an error amplifier. It's better to draw that also. So there are different types of phase detectors: analog type and digital type. That is analog using an analog switch, digital using symbol XOR gate, and also flip-flop as a phase detector. So now you can see what are the applications of PLL. PLLs are used for AM detection, FM detection, frequency division, frequency multiplication, and frequency convert as a translator of frequency. Of course, we can use the PLL circuits that we can discuss in the next class. Okay.